Hi there! Welcome to the astronomy class. Large-scale filaments are the unexplored link between high-density environment of galaxy clusters and the sparsely populated field. The large-scale filaments can extend up to hundreds of megaparsec and are several megaparsec wide. In this video, we will discuss about these magnificent large-scale structures and their influence on the properties of galaxies which inhabit them. Let's begin. As we discussed in one of our earlier videos, the universe is laid out such that all matter in the cosmos lies along large filamentary structures. The environment is quantified as the projected number density of galaxies. The structure of the cosmic web itself can be categorized into three distinct yet continuous environments in which galaxies can live: the clusters, filaments, and voids. Even though clusters of galaxies are the most studied regions of the universe, only about 10% of all galaxies are actually found in clusters, and the majority of the remaining galaxies occupy the large-scale filaments. But this is very recent knowledge even to astronomers, simply because observations are time-consuming and financially expensive. It is only in the last few decades that technology has enabled mankind to explore large areas of the sky more efficiently and at many different wavelengths. The latter becomes important because the distant galaxies are often brighter at short wavelengths such as ultraviolet. This happens due to the expansion of space and stretching of the emitted wavelength with it. This image shows the number of observations taken to map part of a large-scale filament feeding a distant cluster of galaxies. Each of this observation, represented by the red rectangle on the right image, took over an hour of telescope time. The angular size of such a filament increases with decreasing redshift, which means it is more expensive and time-consuming to map large areas of the sky for nearby objects than it is for their distant counterparts. This can be understood from the fact that the Sun and Moon appear to be of similar size even though the Sun is much more farther away. So it is not surprising that research on these large-scale structures in the universe has been possible only in the last few decades after wide-angle redshift surveys such as the 2-degree Field Galaxy Redshift Survey, popularly known as the 2DF-GRS, and the Sloan Digital Sky Surveys came online. By putting together data at many different wavelengths and epochs, astronomers are now beginning to create a complete picture of the distribution of galaxies in the universe and through that hints to the formation and evolution of the cosmos itself. To figure out how the universe looks on very large scales, extensive surveys of the sky have been conducted for decades. During the 1950s, the Palomar Observatory Sky Survey recorded the northern portion of the cosmos on glass photographic plates, each covering a 6-degree into 6-degree area. In this study, 2 plates were made for each part of the sky, recording the red and blue light respectively. This gave an indication of the temperature and therefore the color of the object being recorded relative to their brightness. The glass plate shown here as an example shows the Andromeda galaxy. This image shows the result of a more recent survey of the southern sky made with the United Kingdom Schmidt telescope. This is not a photograph. Rather, this image displays around 2 million galaxies between apparent magnitude of 17 and 20.5 in the B band found within 4,300 square degrees on the sky. Each dot on this image has an intensity ranging between black for 0 and white for 20 galaxies. As you can see, the galaxies are not randomly distributed across the sky. The small bright regions in this image are clusters of galaxies and the longer filamentary structures represent the superclusters. A supercluster is a three-dimensional distribution of galaxy groups, clusters, and filaments. It is believed that there are around 10 million superclusters in the observable universe. This image here is a slice cut out of the three-dimensional universe. Every single point here is a galaxy, the distance to which has been measured using the spectrum by the Sloan Digital Sky Survey. We are at the center, and as far as we can see, the distribution of galaxies in the universe is very filamentary, and several large concentrations such as these superclusters become evident. The human eye and brain are trained for finding patterns even when they don't exist. In case of the large-scale structure of the universe, the problem is compounded because it is a two-dimensional representation of the sky. All the galaxies distributed in a three-dimensional space are projected onto the plane of the sky, so true associations cannot be distinguished from line-of-sight coincidences. Three-dimensional structures may be hidden or distorted when flattened on two dimensions. So in the 1980s, several groups of astronomers began making three-dimensional maps of the universe by using the redshift of galaxies and the Hubble's law to provide for the distance of galaxies. Since then, several redshift surveys have been carried out to varying depths. These surveys reveal the presence of gigantic voids which are vaguely spherical in shape and extend up to 100 megaparsec in diameter. More recent observations using deeper data, however, reveal that voids may not be completely devoid of galaxies. This means the deeper we look, more galaxies we can discover. So whether voids are an observational illusion or reality is really an issue of debate. But for now, astronomers believe that voids are real structures even though they may not be completely empty. They are regions of space with extremely low density of galaxies bounded by large-scale filaments on all sides. Major credit in our current understanding of the large-scale structure of the universe is due to Margaret Geller and John Hookra of the Harvard-Smithsonian Center for Astrophysics, whose far-sightedness and skillful efforts changed our understanding of the cosmos. Most surveys carried out in the 1980s sampled just one area of the sky, so it was not possible to get an overall picture of the general distribution of galaxies. In order to resolve this, Geller and Hookra, along with their co-workers, carried out surveys of wedge-shaped slices of the universe. This was like making parallel cuts through a block of Swiss cheese. This technique very well showed regions which were empty and how they were connected to one another. This image is one of the first slices from their survey completed in the year 1985. Because of the uncertainty in the value of h0, the Hubble constant at the time, the distance here is expressed in terms of the radial velocity cz, where z is the measured redshift and c is the velocity of light. Each dot on this plot is a galaxy. Pause the video here for a minute and try to study this figure. Imagine a three-dimensional distribution of galaxies that would have this cross-section. Clearly, the galaxies are not randomly distributed. The slice also shows that galaxies do not form a network of thread-like filaments which meander through the space. If they did, then a slice would be much more likely to cut across a filament than along it, just like if you would cut a bowl of spaghetti into two. There are simply too many connected features and too few isolated clumps for this to be true. You can also see very clearly that a slice through a froth of soap bubbles or foam sheet would look something like this. So in conclusion, these slices showed for the very first time that galaxies lie on two-dimensional sheets that form the walls of bubble-shaped regions of space. Inside those bubbles, there were huge voids. The human-like figure that you see in this slice is actually the coma cluster that we have introduced in one of our earlier videos. The Sloan Digital Sky Survey, ongoing since the year 2000, is one of the most ambitious and advanced deep surveys of the universe. The very first phase of this project, completed in 2005, imaged more than 20% of the sky at 5 wavelengths between 3000 and 9000 angstroms and recorded around 200 million objects. To date, the Sloan Digital Sky Survey has imaged and taken spectra of more than 900,000 galaxies and over 120,000 quasars, along with more than 200,000 stars. This visualization presents a three-dimensional view of the largest structures in the universe using data from the SDSS. It provides a three-dimensional map of about 1 million galaxies and quasars. As the survey progresses, the data are released to the scientific community and the general public in annual increments. The Sloan Digital Sky Survey utilizes a 2.5-meter telescope on Apache Point in New Mexico in the United States of America. Its 120-megapixel camera can photograph 1.2 degrees of the sky at a time. This is 8 times the area of the full moon. Now, when the survey has covered almost one-third of the sky, the SDSS has produced the most extensive map of the universe, showing a detailed view of the large-scale distribution of galaxies in the cosmos. It is not easy to imagine how the pattern of galaxies revealed by the redshift surveys could have come about from initially random distribution of galaxies. By chance, of course, some areas would have had more galaxies than others. The denser regions gravitationally attracted even more galaxies, leaving the less dense volumes even less denser or empty. Although gravity acts to increase the difference between the high and low density regions, it is not enough to explain the size of the gigantic voids. The largest voids are around 100 megaparsec across, but the peculiar velocities of galaxies are only on the order of a few hundreds of kilometers per second. Using the typical peculiar velocity value of around 600 kilometers per second, the time for a galaxy to cross a void would be 160 gigayears. This is much longer than the average age of the universe, therefore implying that the galaxies could not have formed inside the voids and then moved out. Instead, the galaxies must have formed almost in their presently observed pattern. This inference further implies that the seeds of the distribution pattern we see today were present from the earliest moments in the universe when the first structures came into existence. The large-scale filaments are special not just because of their omnipresence in the universe, but also because they accelerate the evolution of galaxies traversing them. Research, including my own work over the last 3 decades, evidently shows that galaxies on large-scale filaments interact with each other gravitationally. This is a natural consequence of the fact that even though galaxies are moving in the same direction, that is, towards the nearest cluster, the density of galaxies on filaments is sufficient to trigger gravitational interactions amongst them. This leads to a burst of star formation in the galaxies, which in turn utilizes the cold gas present therein. Such a galaxy will exhaust its gas even before it encounters the hostile environment of clusters that we discussed in our earlier video. As a consequence, such a galaxy would turn optically red in color and evolve passively in the cluster. In due course of time, as majority of the stars begin to age, the morphology of such a galaxy will change and it will turn into a passively evolving elliptical, which are observed in present-day galaxy clusters. Let's try to understand this using a simple analogy. Imagine a long path leading to a castle. These large-scale filaments are synonymous to such a path leading to the deep potential well of massive galaxy clusters which are capable of attracting several galaxies in their vicinity. Note, however, that all the galaxies on a filament are moving along the same direction, just like the traffic on a highway, and therefore the chances of mergers between these galaxies are almost negligible. But due to the influence of gravity, they can still interact with each other while moving along the same direction, that is, towards the center of the cluster. Using multi-wavelength analysis of galaxies in and around clusters, astronomers find evidence of enhanced star formation activity in many galaxies further away from the center of clusters. In a 2012 study conducted by our research group, we found that when galaxy clusters are split into 2 categories, such that one of them had at least one bright, high star formation galaxy called as a starburst close to its periphery, the stacked distribution of star formation rate as a function of the distance from the center of the cluster showed an enhancement in the average star formation rate of galaxies on the boundary of clusters relative to the control sample. This led us to conclude that galaxies assimilating into clusters is equivalent to cars on roads traversing a roundabout. The typical density of cars in such a situation is higher at the roundabout relative to the roads, simply because many roads are leading to the roundabout. This is exactly what is happening on the periphery of the galaxy cluster as well. As galaxies on different filaments come together in a small region of space around the boundary of the cluster, the likelihood of gravitational interactions and consequently triggering of a burst of star formation in them increases, leading to higher star formation in such galaxies. Further analysis in this study showed that clusters with star-forming galaxies on their outskirts are actually younger relative to the control sample of clusters. Similar results have been obtained by many studies using optical, infrared, and ultraviolet data since then. More recent results reveal that properties of filament galaxies also change as a function of their distance from the central axis of the filament. Assuming filaments to be cylindrical, it appears that galaxies become redder and more passive closer to the central axis than they are away from it. These findings, however, are yet to be confirmed with deeper data for statistically large samples of filaments. As you can imagine, filaments are not straight, and with real data, astronomers only have the two-dimensional distribution of galaxies to work with. So which structures can be called a filament? How long are they? How wide are they? These are some of the questions that astronomers need to answer when they start out to analyze the impact of the filament environment on galaxies' properties. Many astronomers are trying to find the best techniques for identifying these large-scale structures. While some of them are using galaxies, others are searching for the intrafilament medium, which is the warm gas believed to be filling the filaments, just like the intracluster medium pervades galaxy clusters and influences the properties of galaxies therein. New X-ray observing facilities are now helping astronomers in achieving this goal. In a 2020 study, Tanimura et al. Found evidence of warm-hot intragalactic medium in a stacked analysis of large-scale filaments using data from the eROSITA and other X-ray missions. More recently, another study based on the eROSITA data discovered an X-ray filament which is longer than 13 megaparsecs and connects two galaxy clusters, Abell 3667 and Abell 3651. Astronomers are also using galaxies to explore other properties of filaments. For instance, a 2021 study claimed to have found the evidence to support that filaments with massive clusters at either end are spinning about their long axis. It is important to point here that while filaments with massive clusters at either end are easier to find, this may or may not be the only condition for a filament to exist, which means a filament might exist even without having a cluster at one or even both its ends. In conclusion, we have just begun our quest to uncovering the mysteries of the large-scale filaments, and I am hopeful that with the state-of-the-art observing and computing facilities becoming available, astronomers will soon be able to better understand the evolution of galaxies in the cosmic web. I hope you enjoyed this little introduction to the filament environment and how it influences the properties of galaxies. Please let us know what other topics you would like us to cover on this channel, and do share our content with other astronomy enthusiasts. I'll see you in the new year. Until then, take care.